Welcome back to the last video of the Active Learning video series. My name is Frankie, and in this last video, we're going to close the Active Learning video series out with applications and limitations. So I really want for you to understand how to implement active learning and to see other people's implementation of active learning. And we'll have a discussion about when to use it, what the limitations are in active learning. The basic problem that active learning is trying to solve is learning a target-output distribution as a function of an input space. And active learning does this in an iterative, sequential way by adding more data to a training data set. So we assume that in your problem, you have plentiful access to unlabeled data. And maybe the reason why you're using active learning is because it's costly to label your data. To implement active learning, there are some requirements imposed on your system. So as a reminder, this is a flow block diagram of an active learning algorithm of the different signals and processes involved in implementing active learning. So their first requirement is you need to have the ability to annotate on command. This is an iterative process, and so it's a while loop. It's cycling through these different processes, and one of those blocks is an annotator. We require that in active learning, your query policy can ask your annotator to transform an input into an output through some kind of simulation or measurement so that you can append it to your training data set. Also, we require embedded real-time computing because once the training data set is passed to the learner and the query policy, there's some computation involved in learning the input to output from the training data, and there's also computation required of the query policy to calculate where to sample next. Some advantages that we talked about in video 1 in more depth included improved accuracy. In active learning, you are trying to learn your input to output transformation as efficiently as possible. And implicit in that is that you are sampling in an intelligent way that will achieve faster convergence. That means that you're getting to a good solution sooner with less samples. Implicit in that, a consequence of using less samples is that you reduce your labeling costs because you have fewer samples to label. And then if you're interested in improving generalization, active learning samples in such a way that increases dissimilarity or disagreement between samples. And you can go to video 3 for a discussion on the different query policies that optimize for different information criteria. And then finally, if you use probabilistic models, you can be robust to noise, and we touch on that in video 3 about learners. If you put all of these 3 components together of what kind of basic problem active learning addresses, the kind of requirements that are imposed on your application if you use active learning, and then the advantages that you could get from active learning, then at the intersection are the applications that are well suited for active learning. Let's talk about a few applications. This is going to be the set of slides where we go through specific instances of active learning implemented in the wild by some real researchers. And as you can see, we're going to be talking about some very diverse applications and some range of goals associated with active learning. So first, we'll talk about lunar resource prospecting, remote sensing vegetation mapping, then material science, property prediction, air quality monitoring, and then system identification of dynamic systems. So you can see that there are some space applications, some Earth applications, and then down to different length scales of, so let's see, material science is at the molecular level, whereas air quality is at the meters, kilometers length scale. The different goals include prospecting, mapping, prediction, monitoring, and then characterization. All of the slides are going to be laid out like this, where we have all of the components of the active learning algorithm in the blocks that we've labeled familiarly. And what I want you to notice is that like we said in video 3, the data in the annotator are tied to the application and are strictly set when you go into the problem. But what can change are the learner choice and the query policy choice. So for this first paper, this is a paper from my lab where we were prospecting for lunar resources. We had data from an annotator called the Lunar Reconnaissance Orbiter. It was a satellite that flew over the lunar surface, and it had a payload on board that measured the amount of water ice at a certain location. And so that was the problem that we wanted to solve. Can we map the surface of the moon, map the amount of water ice on the surface of the moon associated with its position? So the transformation problem is position to water ice. And the way we chose to learn this distribution was with a Gaussian process. And the query policy that we decided to implement was with an uncertainty sampling query policy. We're using that Gaussian process variance to select where LRO should sample next. And you can find more at this link at the bottom. I chose to open with this application because I'm familiar with it, but this is one of the simplest implementations of active learning possible, where the Gaussian process is not only the learner, but also the query policy. In the next application of remote sensing for vegetation mapping, the authors were using this radiative transfer model simulation to take in spectra at a certain location and then transform it into a leaf and canopy parameter. And so you can see some very pretty pictures from that paper. The learning model that they chose to use was a Gaussian process. And then the query policy, note how it's different, is the diversity sampling query policy, where they use the cosine similarity of samples. So remember, uncertainty sampling is when you are increasing variance across output. Cosine similarity is the variance across input. Already starting to see some mixing and matching from the components we were talking about in video 3. For this application of material science property prediction, the authors seeded a data set using the Materials Project Database, which is a very cool open source database that you can Google and access all of this information yourself right now. The problem statement was to take a molecular structure and then to map it to formation energy. And you can see the author's depiction of how to do that. There are 2 dimensions of the input space shown here, and then the formation energy is mapped in this color bar. The authors decided to build a learner that had not only a convolutional neural network, but also a Gaussian process appended to the end of it to be that learning model. And the convolutional neural network probably was due to the structure of the information going in from the data set. But then the Gaussian process was very strategic because it was used in a query policy of uncertainty sampling. For this application of air quality monitoring, we have a problem statement of trying to figure out what the air quality index is at a certain location. This map was generated by the authors who are from Beijing, so it's a map of Beijing, and each pixel, which is like a designated square area in Beijing, the color indicates the air quality at that certain location. Previously, the other applications we saw were universal approximators, but in this particular application, we see a domain-specific model. The authors used a Gaussian air pollution dispersal model, which is very specific to their domain, and trained it with an expectation maximization algorithm. For their query policy, they decided to use a diversity sampling, so a cosine similarity where they compared the basis vectors over the grid samples. And they had a really cool annotator where they had a network of users with smartphone sensors that they, from the query policy, they requested folks in certain places in the geographic area to give a sensor measurement, and that's how they were able to incorporate measurements into their training data set. So really cool implementations of applications. The last application is system identification of dynamical systems. And so this is a paper also generated from my lab from a PhD student that I work with, Hans Mertens, who will give a full talk on this paper. But in essence, we were trying to look at modeling the dynamics of various systems. Pendula, a two-tank system, a Lorenz system, and we wanted to see what the impact of different learners, like a Bayesian neural network or a Gaussian process, may be on learning the dynamics of a system efficiently. The query policy was held constant despite switching between Bayesian neural networks and Gaussian processes, and our annotators were simulations of the dynamical systems of interest, like a pendulum, a two-tank, a Lorenz system. So I've asked him to give a talk, and his talk will be posted as a part of this series at the end. So cool applications, but how do we compare the active learning performance compared to other sampling strategies? So I think that other sampling strategies that are worth comparing to or act as baselines are grid sampling, which is where you have your region of interest, but then you discretize that region of interest into a grid, and then you measure the output at each one of those grid locations in the input space. Random sampling, you take your region of interest, but you stochastically, randomly sample from that space. And so you can have variable distance between the different points that you sample. And the way that I think that we should measure performance is with this column, with guarantees. So active learning has shown some empirical results as to the way that algorithms perform, whereas grid sampling and random sampling do not have any guarantees about how your algorithm is going to perform. Samples until convergence, active learning has shown to not need that many samples to converge to a good model. Whereas grid sampling is exhaustive. You're going to discretize and sample all of those points, and so the samples are just immense. And for random sampling, it's hard to say because random assumes some probability, but there is no intelligence or strategy with random sampling, so it's probably high for the number of samples until convergence. For active learning, convergence accuracy is high because you can set your optimal stopping condition to target a certain accuracy. And for grid sampling, the convergence accuracy is going to be high because you're doing an exhaustive search, and random sampling, again, probably high due to its probabilistic nature. For computation time, this is where active learning suffers. Because active learning has some intelligence, that necessitates some computation. So you can look more in depth into video 3 when it comes to the learning models and the query policies, the amount of computation that your active learning algorithm will necessitate. But for grid sampling and random sampling, these sampling strategies are defined ahead of time, so there's no real-time computation that's necessary. It's just set it and go. Active learning doesn't always perform better than all sampling strategies. There are limitations, and I might pose this more as directions for open questions. So As we talked about in the last slide, there are some empirical observations of guarantees, but there aren't any analytical guarantees, not in a robust way. So that is something that I pose to you all watching this video, so you can work on that, please. Active learning, because there is some structure associated with active learning, this may impose requirements on the type of models that you get to work with. Further, if you then have to choose the different models or even the query policies that you work with, there may be bias introduced with the models that you select. Finally, computation and complexity can become prohibitive. So, like we were saying in the last slide, computation is something that's necessary in active learning, whereas it's not necessary in naive sampling strategies. All right, so if we reframe these into some open questions, and maybe even if there are not limitations, here are some open questions that we would love to see you work on. So, analytical guarantees. Additionally, interpretability of active learning algorithms needs some work. Active learning algorithms are hard to describe in behavior because there are these iterative processes in which a future decision then cascades into a set of future trajectories of where an algorithm could go. So interpreting that kind of behavior has been difficult. We'd also love to see optimal or adaptive query strategies that are affiliated with a model or a data type. If there's any kind of formal strategy to associate query with model and data, that'd be a great solution. In video 3, we talked about value of information in query strategies, but we didn't really talk about incorporating cost in query strategies. So there has been some work done in this, but we'd like to see way more inclusion of cost in query strategy, because in real life, there very much is a cost associated with sampling. We'd also like to see more scalability in the large data regime. We were talking about how in video 3, the learning models and some query policies are subject to the curse of dimensionality. So maybe there are some really neat engineering or applied math tricks associated with these models or query strategies. For active learning, we talked about in this video series singular objectives. There was just one objective function that you had to optimize for. But what if you had multiple? How then do you make the trade-off in your query policy to satisfy many objectives? Further, what can we say about the model that active learning had learned on this data set, and what then can we say about on a different data set or in a different domain? And then finally, just like many machine learning communities, the pace of work has gone so quickly that it's hard to create standards that are adopted by the community. So we would love to see more standard evaluation metrics in the active learning field. If you're interested in implementing active learning for yourself, I will leave you with some common software packages. Many of them are in Python, as you can see, but there are a couple of packages in R and in MATLAB. All of these have links, which I will put in the YouTube description, except for the MATLAB package, which is behind a license. So I hope that you learned something about active learning, and I hope that I inspired you to maybe think about how to apply active learning for your application. This is the end of our video series, and I hope that you stick around for Hans's talk. Thanks so much.